Okay, welcome to the discussions of ethers and epoxides. We'll also be discussing about thiols and sulfides as well in this lecture. This comes under chapter 18 of John McMurray. This is a video produced by Chemistry and Biochemistry Department, University of Massachusetts, Dartmouth. It is for the benefit of Organic Chemistry 2 students. These are the topics that we'll be covering in this chapter. We'll be briefly discussing about the nomenclature of ethers. We'll look into the synthesis of ethers, and then we'll discuss about some of the reactions of ethers, especially cyclic ethers called epoxides. We'll also be discussing about sulfur compounds. These are the things that you should be able to do at the end of the chapter. Okay, so please go through this, and you can expect questions on these skills in the exam. Okay, anyhow, the nomenclature of ethers, epoxides and sulfides. I'm not going to discuss the nomenclature of thiols because we have dealt with that in the chapter of alcohols. So thiols are synonymous to that of alcohols in their structure, except that oxygen is replaced by sulfur. This also has two pairs of electrons on sulfur, whereas oxygen has two pairs of lone pairs of electrons. If alcohols are regarded as monoalkylated water derivatives, you can regard ethers as dialkylated derivatives of water. Both the hydrogens of water have been replaced by two alkyl groups. If both the alkyl groups are symmetrical to one another, if they are same, you call them as symmetrical ethers. And there can be mixed type of ethers where one alkyl group is different than the other alkyl group. Here we have an aryl group, so it could be aryl alkyl ethers, alkyl ethers, or symmetrical ethers of this kind. Okay, some of them could be cyclic ethers. What you have seen here is cyclic ether, which is called tetrahydrofuran. Furan because it's derived from parent heterocycle, which is furan. If you hydrogenate furan completely, you get tetrahydrofuran. That's a good solvent. We'll talk about some of these things in when we get to cyclic ethers. The other cyclic ether that we'll be focusing more on today's class would be epoxide, which is a three-member ring. Because of the ring structures, there is a little bit of chemistry to this ether than to this ether. Ethers are regarded as boring functional groups because there's not much of chemistry. In a way, it is good, right? We don't have to deal with too much of chemistry. Anyhow, but there are some properties, physical properties that we need to talk about because ethers are widely used as solvents in organic synthesis. When you come to the sulfur version, if you have SH, you call them as thiols. If you have two alkyl groups on the sulfur, we call them as sulfides. These alkyl groups could be again similar to one another, or they could be mixed alkyl groups, as you can see here. This is diethyl sulfide, this is diethyl ether. Just you substitute ether for sulfide when you see sulfur. This is tetrahydrothiophene. Again, this is derived from thiophene, so it's called tetrahydrothiophene. Okay, so ethers can be regarded as dialkyl derivatives of water or alkylated derivatives of alcohols. You are alkylating the other hydrogen with an alkyl group, so you get ether. Okay, sulfides can be regarded as derivatives of thiols. Okay, alkyl derivatives or aryl derivatives. Nomenclature, you can name them as ethers. So if just find out the two alkyl groups attached to the oxygen, alphabetize them. Ethyl, methyl, ether. Ethyl, methyl, ether. That's a common name. It's not an IUPAC name. Here we have chloropropyl because there is chlorine on the propyl, and there is an ethyl, so it's called 3-chloropropyl ethyl ether. Diphenyl ether, diethyl ether. When you have two symmetrical ethers, two similar alkyl groups, you can use the prefix called di and then put the alkyl group and then place the functional group at the end, suffix. Okay, so for example, diethyl ether, diphenyl ether, diisopropyl ether. If you have two butyl groups, you can call dibutyl ether. Okay, So name the groups attached to oxygen in alphabetical order as separate words, and ether is the last word. Okay, it's not IUPAC nomenclature, that's what you should remember. We are just naming them as functional class. It's kind of common nomenclature. If you want to name it as IUPAC version, you have to follow this methoxyethane is other way of naming this ether. Otherwise it was ethyl methyl ether, right? So you can name them as alkoxy derivatives of alkanes. So you are treating this as ethane as a parent molecule, and you are regarding this as a substituent. That's why it's called methoxyethane. So you choose the longest chain first, and then the small substituent is going as a substituent. Okay, small alkyl group is going as a substituent on the oxygen. So this is a parent alcohol, right? So that's this is regarded as substituent, so parent alkane. That's why it's ethane, methoxyethane. 1-chloro-3-ethoxy propane, ethoxyethane. This is naming them as alkoxy derivatives of alkanes. Okay, so sulfides, just replace the ether word with the sulfide. This is methyl ethyl group. So ethyl comes first on alphabetization. So ethyl methyl sulfide. This is diethyl sulfide. This is methyl cyclopentyl sulfide. When you alphabetize, cyclopentyl methyl sulfide. And if you were to name that as a substituent, so this whole thing has become substituent. So methyl thioethane. Okay, thio is for sulfur. Okay, that's where it's got oxy is for oxygen, thio is for sulfur. Ethyl thioethane, methyl thiocyclopentane. These are some of the cyclic ethers that you see here. Their names are normally derived from the common terminology that's in the practice. So you can go into the etymology and see how this are derived. But to mind you, those are not IUPAC nomenclatures. Okay, probably functional groups have been accepted, but these are common names. Oxirane, for example, is 3-membered ring with oxygen in it. Ethylene oxide is a common name for it. Oxetane is when you have 4-membered oxygen containing ring. Oxalone when you have 5-membered oxygen containing ring. We already looked into this as a tetrahydrofuran. This is oxane, only 1 oxygen and 6-membered ring. This is also regarded as tetrahydropyran because this is derived from the hydrogenation of pyran. That's why tetrahydro, that means 2 molecules of hydrogen has been given to pyran, and it results into tetrahydropyran. And there is another molecule, the other oxygen is also in the ring, so it's called dioxane. Oxane is for this ring, so you have 2 oxygens, so you have to now specify the position of the oxane. If you have oxygens in 1,4 positions in respect to one another, we call this as 1,4 dioxane. It could be 1,3 dioxane as well. And there are cyclic sulfides as well. This is called thyrane, thietane, thiolane, thiane. And if you have 2 of these sulfurs, it's called 1,4 dithiane if the sulfur is here. If there is 3 position another sulfur, you would call that as 1,3 dithiane. You come across these in organic synthesis. So some of the examples are listed here. You have a butyl group here and a ethyl group. So alphabetize it: butyl, ethyl, ether. Recognize that these are written as 2 separate alkyl groups, and then ether is coming as a suffix. And in the IUPAC way, you have to recognize the small alkyl group as a substituent, and the parent alkane chain is given by this. So it's called ethoxybutane, and you don't have to mention the position because there's only one. If you want to mention it, you can mention it. Even if you say ethoxybutane, this is what is ethoxybutane. 1 ethoxybutane is much more non-ambiguous. Okay, and this is bromomethoxy containing cyclopentane. But just that now you have 2 groups. Bromides get higher priority than ethers. So 1 bromo, 2 methoxy, cyclopentane. Cyclopentane is the parent hydrocarbon. And you have an alkene here, so the geometry has to be mentioned. And this is ethyl group, and this is pentenyl. So ethyl Z sorry, G is not pentenyl, propenyl. G propenyl ether. Okay, that's a common name. Two alkyl groups, ethyl, and this is other alkyl group. If you want to name this as IUPAC name, Z 1 ethoxy 1 propene. 1 ethoxy 1 propene. Diethoxy 2 cyclohexenol. 2 ethoxy groups, and there is a cyclohexenol. So it's kind of IUPAC nomenclature. This is not quite diether, so it's kind of acetal functional group, but nevertheless they can name this as a diethoxy compound. Okay, and here is an epoxide. We already saw that these are called oxiranes. This epoxide is trans. Let's say if we were to take this oxygen off that, this is where the alkene would have been. So this is derived from the alkene, trans alkene, so or E alkene. So you have to mention the geometry of that. The configuration of the two alkyl groups are opposite to one another, so it's called trans epoxide or E epoxide. E 2-methyl 3-hexene oxide. 2-methyl. You have to now regard this whole thing as a parent chain, and this as a side chain. So in that second position there is methyl group that's listed here, 2-methyl 3-hexene. Third position there is where the oxide is, and that's where it would have been double bond. So this is regarded as oxide of the alkene. So that's one nomenclature. 2-ethyl 3-isopropyl 2-ethyl 3-isopropyl oxirane. Trans, because this is trans in position. So this is named as oxirane, and now you are just substituting them. The bigger alkyl group is 3-isopropyl 2-ethyl. The numbering is starting from oxygen 1, 2, 3. 2-ethyl 3-isopropyl oxirane. Even if you were to reverse the numbers, that would be same structure, right? So probably it's going by alphabetization. So 2-ethyl 3-isopropyl oxirane. Oxirane is regarded as a parent heterocycle here. In this nomenclature, this is regarded as alkene oxide. So you imagine that there is an alkene, and you name that oxene and that alkene, and then add oxide as a suffix in common nomenclature. Okay, so this is 2-methyl 3,4 epoxy hexane. This is much more unambiguous nomenclature. This is probably IUPAC nomenclature. So here again you are recognizing the parent side chain, parent chain, and this is the side chain or the substituent. So you are locating the locant of that methyl group inside the second position. So 2-methyl E, that's the configuration of the epoxide, and this is 3 and this is 4, so that's where the epoxide is attached. So 3,4 epoxy hexane. So there are more than one way is to name the epoxide, so you have to be familiar with at least a couple of those. This could be the most unambiguous IUPAC nomenclature, but nevertheless none of them are wrong. Everything is correct. Okay, so this is cis, because this is cis epoxide. The epoxide has both the alkyl groups are going on the same side. Cis 3-methoxy cyclopentene oxide. This is a methoxy group, and cyclopentene, because this is where the oxide is, double bond would have been, so that's cyclopentene. It's an oxygenated compound of alkene, so it's regarded as oxide of alkene, so that's what is seen here. The other way, cis, that's the geometry of the epoxide. 3-methoxy 1, 2 epoxy cyclopentane. So the number is going in such a direction that the substituent is getting the lowest number possible. Okay, and that's about nomenclature. The epoxides and alcohols are very commonly encountered in natural products. Even the ethers are commonly encountered. We have already seen some of those functional groups when we saw alcohols. Here are some couple of examples where epoxide is part of a natural product. This is an anti-cancer drug called epothelone. It has alcohols also inbuilt, and there are some epoxide functional groups, and this has 2 epoxides. Okay, so the epoxide containing compounds are very biologically active because because of the epoxide. It's a very strained ring and it is bound to interact with the biological systems. So epoxides have some biological relevance, so we need to know the chemistry of epoxide. Before looking into the chemistry, we should look into the structure and bonding, because the chemistry of epoxides, or any for that matter any particular functional group, is influenced by the structure and bonding, or the structure and bonding dictates the chemistry of the functional groups, and it is so even in ethers, in the epoxides. So we'll first look into the structure and bonding. As we looked into the water structure when we looked in alcohols, and the more bulkier the groups you substitute this hydrogen with, the bond angles are going to increase, because they are bunch of electrons. You cannot force two alkyl groups close to one another, so they repel, and as a result this bond angle increases compared to water. For example, in alcohols we have 108.5 degrees. This is an sp3 hybridized carbon. There are two sp3 orbitals with two pairs of electrons. So you got to remember that there is as such a repulsion between those two pairs of electrons, but that's the reason why this is deviating from sp3 hybridization bond angle, which should have been 107.5. And the more the bulkier groups we bring in onto the oxygen, the bigger the repulsion between the bulkier groups. So now these two electron pairs are smaller compared to these two, so the bond angle expands a bit more than what you saw in alcohols and water. Okay, so diethyl ether has a bigger bond angle, and ditetrbutyl ether has a bigger bond angle than dimethyl ether. Okay, so nevertheless it's an sp3 hybridized oxygen, so the shape is tetrahedral, if you count these lone pairs as well. Okay, otherwise it looks like a bent molecule of what is shown here, but the actual structure is shown here. Okay, so there are two pairs of electrons on oxygen. Even if you don't explicitly show them, you have to recognize that there are two pairs of electrons. When you write the mechanisms, structures, you better remember that, or you just depict it here so that you would not be misled. How does it influence the structure of an alkane? How does an oxygen influence the basic skeleton of the alkane? It does not alter much of the structure of alkane. It's still written in a zigzag form. One of the CH2 is replaced by oxygen, and still all those things that you learn in conformational analysis would be valid here as well, because it's the structurally oxygen is replacing CH2, and it's not doing much to the structure, just that the bond angles are a little different here depending upon the groups, but nevertheless it's still a tetrahedral atom in group, so the whole geometry is intact. If you were to replace one of the CH2 of cyclohexane ring with an oxygen, you would still see those boat conformations and chair conformations that you learned. So still the tetrahedropyran, for example, where one of the oxygen is replacing the CH2, would be stable in cyclic chair form than in boat form, because all that interaction that you learned are still in place here. Okay, so the conformationally CH2 oxygen does not alter much of the structure compared to the parent hydrocarbon. Okay, any questions? If not, let's look into the properties. We just now looked into the structures, we saw the bond angles, we saw the lone pairs, and how do the physical properties get affected because of these structural features. So this is the ether that we are discussing. These are the ethers, two ether molecules. There is no hydrogen bonding here, though we have an electronegative oxygen, and that would act as an acceptor, but there is no donor. Donor should have a hydrogen to donate. Acceptor should accept the hydrogen, which is the case in alcohols. One molecule of alcohol is acting as a donor of the hydrogen, the other molecule is accepting the hydrogen, so you have hydrogen bonding, and as a result the boiling points and physical properties of alcohols are affected because of the hydrogen bonding, whereas we don't see that hydrogen bonding here. So ethers are low boiling compared to alcohols, and they are volatile. If you were to mix them with alcohols, then there can be hydrogen bonding, which is called intermolecular hydrogen bonding. You have an acceptor in the form of this oxygen, you have a donor in the form of this hydroxy group, so there can be hydrogen bonding. But nevertheless, ethers by themselves do not have hydrogen bonding. Okay, that's the reason why when you compare ethers of the same formula almost, right, this has C2H6O, C2H6O. So the formula, molecular weight formula, for molecular formula, they're all similar to one another. But look at the boiling point of methanol, it's at 78. Look at the boiling point of dimethyl ether, which is a gas. Basically at room temperature you cannot have methyl ether in your flask, right? So in other words, though they are constitutional isomers of one another, the boiling points are drastically different. That can be attributed to the lack of hydrogen bonding in ethers. Alcohols have that hydrogen bonding. So excuse me. So that's something you have to keep in mind. So the boiling points of all ethers are much close to that of alkanes than to that of hydroxy compounds, because alkanes do not have hydrogen bonding, and so are ethers. So their boiling points are close to one another, though there might be a little bit of dipole moments because of the oxygens, but nevertheless their boiling points are not altered very much compared to one another here in between these two. But when you compare these two, there is a drastic difference in the boiling points that's attributed to hydrogen bonding. And their miscibility in water. If you were to dissolve this alkane in water, it would not at all be miscible. You cannot find any of these molecules in water layer. They would just form two separate layers. So does ether, but there you can find small amounts of ether in water, because ether has lone pairs and it acts as a donor of electrons, or it acts as an acceptor of hydrogen bonding, and so water can donate a molecule that can form hydrogen bonding with this ether. So you find small percentage of ether miscible in water. Okay, so does alcohol, because we have hydrogen bonding. That's, you can find much more percentage of this alcohol in water than you would find this one or this one. Nevertheless, ethers are miscible to some extent in water, and hence they are soluble to some extent, whereas alkanes are not soluble. Okay, and I'm going to skip this slide. Again, hydrogen bonding is the driver of physical properties. They are less dense compared to water, so they form top layer when you mix with the water, and because of the electron pair on oxygen, they are good solvating solvents. So they are good organic solvents for organic synthesis, and so you can extract non-polar and polar compounds by using ether. Ether forms a top layer when you are extracting from water, so you can easily separate your organic compounds. So the main use of diethyl ether is as a solvent in organic synthesis. There's not much of chemistry available to diethyl ether, because the ether group, as I said, is devoid of much chemistry. They are called boring functional groups. Okay, why do we use ether as a solvent? And as I said, it's a good solvent because not only it can extract both nonpolar and polar organic compounds, it readily separates from water, and so it is very low boiling. When you do an extraction, you got to get rid of the solvent. So if you have a higher boiling solvent, its removal would be difficult, whereas ether has a lower boiling, so you can easily remove it. At times this can be problematic too. So it's not a good solvent for reactions, it's a good solvent for extractions. In reactions, you would rather prefer to have a higher boiling point, then you have to go for a higher alkyl groups on this ether. Okay, so nevertheless, diethyl ether is a good solvent for extractions. How about cyclic ethers? Cyclic ethers are more miscible in water than acyclic ethers because of their compact shape, and they can easily participate in hydrogen bonding. So tetrahydrofuran, dioxane, such solvents are completely miscible with water. If you were to mix tetrahydrofuran 500 ml and water 500 ml in your separatory funnel, you would not see two layers, you would only see one layer mostly, because tetrahydrofuran would be quite miscible with water. So that could be disadvantage or advantages at times as you need. Okay, so tetrahydrofuran has a higher boiling point, so that's a good solvent for reactions. So is 1,4-dioxane. So these two are also ethers, but they are cyclic ethers. So the main use of ethers is as a solvent. There are different types of solvents that we learned already in the organic labs. So there are protic solvents and aprotic solvents. There are polar solvents and apolar solvents. There are protic, polar, protic, apolar solvents. Okay, so there are all sorts of classification, right? So where does ether fit into this classification? Ether is regarded as aprotic because it does not have any proton to donate, and it's somewhere between polar and apolar. It's not as apolar as alkane is. At the same time, it's not as polar as a hydroxy solvent is, like ethanol. So it's somewhere, it strikes a middle ground between the polar and non-polar solvents. It's an aprotic solvent. So there are advantages of using ethers, especially when you are doing any metal ion chemistry, because metals can be solvated using ether lone pairs. So 6 of these ethers are lined up and they are solvating one lithium ion here. So the lithium salts can be easily dissolved in ether to some extent than in any other solvent because of the solvation. The cations can be solvated using ether, anions are left alone, so this anion can go on to do some other reaction. For example, substitution reactions. This is available for substitution because it's not solvated, and moreover the counter ion is solvated, so this is free. So by choosing the solvent properly, you can do some reactions which you cannot otherwise do in other solvents. Okay. And how about alcohols? Alcohols solvate cations and anions both. For example, fluoride is also solvated and lithium is also solvated here. So whereas if you use ether, you can only solvate cations. So people devised new molecules by connecting these alkyl groups. So if, let's say, I'm connecting this R and this R, this R and this R, and if I collect all 6 of them, I can form something like this, right? Like where it's shown here. So this is called cyclic ether. It's called crown ether because it's all the oxygens are lined up as a crown, and their electrons are pointing towards inside, and they can easily trap metals. So these crown ethers are used in metal catalysis in organic synthesis, especially in phase transfer catalysis. Depending upon the number of oxygens in the ring, depending upon the number of carbons, the nomenclature would change. 18 is the total number of atoms in the ring, and there are 6 oxygens, so that 6 is depicting by this letter. Okay, the number of oxygens is shown by this number. The total number of atoms is given by this number. So this would be like 15 crown 5. This is 12 crown 4. Depending upon the cavity size, the size of the metal could be changed. The entrapped metal would be varied. For example, for lithium you don't need this bigger cavity, so you can get away with 12 crown 4 or 15 crown 6. But for potassium and sodium you need a larger cavity size, so you use a bigger crown ether in the catalysis. Okay, so you can go further and talk about this use of crown ethers. They are polyethers, cyclic in nature, and they form stable complexes with metal ions because of the donation of the lone pairs. Metals are electropositive, these are electronegative, so there could be bonding between those two types of species that come in touch with each other. Their applications are normally in phase transfer catalysis, where synthetic reactions need to be done by transferring anion from or cation from one phase to the other phase. Okay, for example, you want to do a reaction with potassium hydroxide and you want to do it in some organic solvent. Potassium hydroxide is not soluble in organic solvent, so you add some crown ether. This solvates the potassium, and this is an organic molecule, so the potassium transfers from one phase to the other phase, and the reactions happen in the interface of these two phases, where the anion would also go along with this species, so you can do some reactions using anions and metals. Okay, so that's why these species are used in catalysis, phase transfer catalysis. If you were to map the electron density, this is how you would see the electron density is more focused and internally than the external side. The oxygens are pointing towards inside, and as a result you can trap some metals here, or so you can solvate some metals. Okay, so for example, potassium is being trapped here. This is also called host-guest chemistry. This is called host, this is called guest, and this kind of chemistry has been used in cleaning up war tanks. I did some of this chemistry in my first postdoc, so I knew the applications of these molecules. We designed some selective crown ethers for removing some nuclear waste. Okay, anyhow, I'm not going to go into the details in the interest of time, but nevertheless, if you were to view the ball and stick models, you can see that there's tight encapsulation of this guest molecule, so it cannot escape unless you break or you work it up with some other strong solvent that can take off the potassium, right? So that's about the crown ethers. You can also regard this as Lewis base and Lewis acid complex. Okay, Lewis acid is the one which is accepting a pair of electrons, and Lewis base is the one which is donating a pair of electrons. So potassium is acting as a Lewis acid here, oxygen is acting as a Lewis base. It's not that oxygen is making 3 bonds here. This bond should not be a solid, it's just an electrostatic interaction. Okay, it's not like a strong covalent bond, so don't get confused. Potassium can have only one electron, right? Because it's only monovalent. So this is just electrostatic interaction. So for example, potassium dissolves in benzene when you add potassium when size cavity, that is 18 crown 6, facilitates the solubility of potassium in benzene. Otherwise, if you add just potassium salt to benzene, they would be immiscible, they would be separate entities. But as soon as you add 18 crown 6, and the solubility of the potassium increases, and you can do some reactions using the fluoride, because the fluoride is available for reactions. Any questions so far? If not, we'll go further. If you have any questions, please see me in my office hours. So potassium by 18 crown 6 solubilizes, complexation of potassium by 18 crown 6 increases the solubility of potassium in benzene, and that is responsible for some of the chemistry that we see in benzene using 18 crown 6. For example, this bromide can be substituted by fluoride. You can do this reaction in benzene, provided if you add 18 crown 6, and you get the substituted product. If you didn't use the 18 crown 6, you wouldn't see this reaction. This is called phase transfer catalysis. And so having seen the properties and having seen the structures of ethers, various types of ethers, we would look into synthesis of ethers briefly, and then we'll go into the reactions of ethers. How do we synthesize ethers? There are a couple of ways to synthesize ethers. One of the ways is to dehydrate one molecule of water between 2 molecules of alcohol. Let's say you have ethanol. Somehow you remove the water molecule from ethanol, you would force ethanol to become ether. Okay, how would we dehydrate it? Hydroxy group is a poor leaving group, so we have to convert that into a good leaving group. So you add strong acid. Acid protonates the hydroxy group. In other words, oxygen donating is an electrons to proton, and it gets protonated, and the protonated species is a good leaving group, so that can leave as soon as it protonates. So as a result, it becomes electrophilic carbon. So the other molecule, some other molecule, right? This is not the same alcohol molecule. This is another molecule of alcohol comes and knocks out this hydroxy group. This is kind of SN2 substitution. If it is primary alcohol, if it is secondary alcohol, you can regard this as SN1 substitution. So this reaction works well when you have primary or secondary alcohols. When you have tertiary alcohols, you would not see substitution, rather you would see elimination, and you would see alkenes forming. That's what we did in the lab last year. We took a tertiary butyl alcohol or some kind of substituted alcohol, and we made alkene out of it, and that's called elimination. Here we are talking about substitution. We are using primary alcohols, and we are dehydrating a molecule of water. This is going as a water molecule, and the rest of it is forming ether. And if you continue the electron push, there is one hydrogen excess here. This is called oxonium ion. Another molecule of water would come by and take the proton off, and then you make a diethyl ether. Okay, so in essence we removed water molecule. So this is H3O plus, but H is coming from acid, so this H plus would go on to do the same reaction again. So this reaction is acid catalyzed dehydration of alcohols. The proton that you are seeing here is not consumed anywhere, it's regenerated. It's used here, but it's regenerated here. So this is acid catalyzed reaction. You don't need equivalent amount of acid, you just need catalytic amount and heat, right? So you can dehydrate alcohols to form ethers. That's one way of making ethers. The other way of making ether is by Williamson ether synthesis. Williamson is the scientist who came up with this method. Here you employ alkyl halides and alkoxides. If you have an alkoxide can act as a nucleophile, and you have a leaving group here. So this alkoxide is substituting this iodide, and this is giving this ether, right? So this is a substitution reaction. As you can imagine, the sterics of this group dictates the product. If this is too sterically hindered, you would not be able to substitute it. You would rather use this as a base, and that would undergo elimination, and you would get alkene, right? So instead of that, if you want to make ethers out of this method, you have to employ primary or the maximum secondary alkyl halides. You cannot have a tertiary alkyl halide. So it does have some limitations and some advantages over the other method. And the other method involves strong acid. Some of the functional groups are not compatible with acid. Let's say you had some other group somewhere in the molecule and you cannot use acid, so you can go for basic method. This is the base, so you add a base to alcohol, it forms an alkoxide, and this alkoxide is now used as a nucleophile, and you add another equivalent of alkyl halide, so that alkyl halide is now electrophilic, and that is where the substitution is happening, and this is a leaving group, and you get ether formed. So what is Williamson ether synthesis? Let's summarize it. Reaction of metal alkoxides with primary with primary alkyl halides and any other leaving groups. It doesn't have to be iodide. Alkyl halides or bromides, iodides, chlorides can be used. It doesn't have to be halide, it can be even tosylate. Tosylate is also a good leaving group. Tosylates are made from alcohols, as we have seen before. You take an alcohol and that use tosyl chloride and it makes tosylate, and that becomes a good leaving group, so one can use tosylate as well here. So what's happening here? The oxygen is acting as a nucleophile, and this leaving group is leaving, and you're forming an ether. So you need an alkoxide, you need a species that has a leaving group in the Williamson ether synthesis. You can make it. This method is good for preparation of non-symmetrical ethers, and this method is probably good for making symmetrical ethers. Okay. This is good for acid sensitive substrates as well, where acids cannot be used. This is because this uses base, so it's kind of complementary to the other method. Alkoxides are normally prepared from an alcohol using sodium hydride or sodium metals, right? So for example, you have an alkoxide here. This is called sodium 1,2,3,4 sodium butoxide plus propyl iodide, and you have to just identify your nucleophile and your electrophile. This is electrophilic carbon, this is nucleophilic oxygen, so draw the curved arrow to that carbon, and then iodide is leaving. So as a result, you form a carbon oxygen bond, and that is shown here. So you made a propyl butyl ether, or butyl propyl ether has been made through Williamson ether synthesis. And as I mentioned, your electrophile should be less sterically hindered. If it is more sterically hindered, this instead of acting as a nucleophile, this would act as a base. We call this as a base when it subtracts a proton from here. We call this as a nucleophile when it attacks here. So this can be base or a nucleophile depending upon what you have at the electrophilic site. So if you were to make a meaningful amount of ether without any side products, you have to use a primary alkyl halide. That's a limitation of this method. How about the stereochemistry? If you have a stereo center here, that gets inverted because this is attacking from the backside. What would happen if I have a stereochemistry here? That stereochemistry would stay intact because I'm not touching this carbon-oxygen bond. I'm just using the pairs of electrons from oxygen, right? So you have to remember that the stereochemistry of the electrophile gets inverted, not the nucleophile. So for example, you have cyclopentoxide here, and that oxide is being added to propyl bromide, and you're making cyclopentyl propyl ether. And how do we make iodides? Iodides can in turn be, alkyl halides can in turn be made from alcohols. So even if you have two alcohols, you can make ether through Williamson ether synthesis, just that you have to convert one of the alcohols into alkoxide, the other alcohol into iodides or halides, and then mix these two in a suitable solvent and let the nucleophilic displacement of this take place. You get ethers. Benzylic halides, allylic halides are good, very reactive, so they give readily ethers. If I had some other substituted alcohols, they are not good in substitution reaction, especially the tertiary alcohols and secondary alcohols, so you would get you would get eliminations. Okay, so you got to tailor your conditions of the reaction such that you favor SN2 reaction and you disfavor E2 reaction, so that you get what you want. If you do it other way around, you get unwanted products. For example, you wanted to do this one, the synthesis of this ether, but however this is very highly hindered, so this benzoyl oxide, instead of acting as a nucleophile, it's acting as a base. So it's just abstracting the proton from the CS3, and this bromide is, these electrons are pushed here and this bromide is taking off. As a result, you get alkene from this, and this is abstracting the proton, so you get an alcohol. You would not get an ether. This is where elimination is favored than SN2. So you have to have primary alkyl halides or less sterically hindered alkyl halides. Let the branching be somewhere else, it doesn't matter, but it matters when the branching is on the alpha carbon of this bromide. That's the electrophilic site, right? So you got to know the limitations and the strengths of these methods so that you can choose the conditions and substrates accordingly to make the ethers. There's another method, especially this method is employed in carbohydrates. You have polyhydroxy compound, you want to convert all of them into ethers, so you just treat that with silver oxide and whatever the alkyl halide that you want to use, especially methyl iodide is more reactive. So these are all acting as nucleophiles. Silver oxide is catalyst. You can make pentamethyl ether or hexam, 1 2 3 4 5 pentamethyl glucose, pentamethyl ether of the glucose. Okay, so silver oxide catalyzed ether formation of carbohydrates is another. This can be used for other methods also, but it's widely employed in carbohydrate chemistry. We'll look into carbohydrate chemistry when we get into the latter weeks of the organic chemistry too. So what else? How else can we make ethers? Can we make ethers from alkenes? We learned in Chem 251 that alkenes can be hydrated using water and some acid. But how about if you substitute water for an alcohol molecule? You would do the first step similar to what you did, that is this is acting as a nucleophile and this is acting as a catalyst. So these electrons are given out to this H plus, and this is carbonium ion formation. So carbonium ion formation goes through the Markovnikov rule, and as a result there is a positive ion at this highly substituted carbon, and this acts as a nucleophile now, and that would attack that carbonium ion, and you get methoxy substitution instead of water substituting, and as a result you can make ether out of this alkene. So this is kind of hydration of alkene, but instead of water you are using alcohol, so you can call this as alkoxylation of alkene. I'm going to skip some of these things. Can we do oxymercuration? We learned that mercury can act as a big proton. It can catalyze the reaction. It can not catalysis. It can give a more more reselective and more chemoselective, more faster reactions when you use mercury catalyst, mercury reagent. This is called oxymercuration, and instead of using water, you are using alcohol, so it's called alkoxymercuration. In Chem 251, you learn oxymercuration, where you would use mercury salt plus water to make alcohols, but here we are using alcohols as a solvent or medium, so you get alkoxylation. So the first step is the same as before. This pair of electrons is acting as nucleophilic, and then it reaches to the magnesium, this mercury, and the mercury gets attached to the least hindered carbon. The positive charge is at the most hindered carbon, and as a result this alcohol acts as a nucleophile, and that goes and attacks the most hindered carbon. You get Markovnikov ether at the end of the day. So let's take an example here. This is an alkene, and you are doing oxymercuration first step, and alkoxylation in the second step, so it's called alkoxymercuration. The mercury baggage is removed using sodium borohydride, because the mercury gets attached in the first step and the alcohol attacks in the second step. In the third stage we need to swap the mercury with hydride, right? So that's why we have sodium borohydride, and make sure that you are writing Markovnikov product here. Okay, so the most substituted carbon is getting the Bohr-methoxy here. So what if you have a cyclic alkene of this kind? You would get oxymercuration, alkoxymercuration, and the substitution is at a highly substituted carbon. Okay, and the sodium borohydride is taking up the mercury and it's swapping for hydrogen. I can do this reaction using H plus as a catalyst instead of mercury. Okay, so or acid as a medium, right? So either you can do addition of alcohols in presence of acid, or in presence of mercury acetate followed by sodium borohydride. So that's another way of making ethers. Alkoxymercuration, alkoxylation of water in presence of acid. What if we have something like this? In the same molecule you have alcohol, in the same molecule you have alkene, and you can do intramolecular oxymercuration using mercurium salts. So first step would be to reaching out to this mercury, and then the positive charge here. So this hydroxy group is attaching to this. This oxygen is giving its electron to this carbocation. As a result, you would form another ring, and you would get a bicyclic compound. It's called intramolecular oxymercuration. So that's some summary of some of the ways to make alcohol ethers. Okay, now let's look into the chemistry of ethers. As such, there's not much of chemistry for ethers. We talked about it again and again. Ethers are relatively unreactive. Their low level of reactivity is the reason why ethers are often used as solvents in chemical reactions, because we don't want something to react. So we want unreactive functional groups as solvents, or unreactive chemicals as solvents. So ether is unreactive, so we use ether as a solvent to extract the compounds to do the reactions. Okay, we don't want solvents to participate in the reaction. We can use solvents to facilitate the reactions, but not as a participant. Okay, then you get solvolysis reactions and all sorts of things. So we don't want them to happen, so we use ethers as solvents because of their unreactivity. And they're also used as protecting groups for reactive hydroxyl groups, because once you protect this hydroxy group, you have an unreactive functional group as ether. So in a sense, hydroxy groups are alkylated to convert them into ethers, and now they don't have any chemistry left for to themselves. So you say that you've protected your hydroxy group. Okay, we talked about that in some of the chemistry that we talked before. There's one side reaction to these ethers that normally happens when you keep them open in the air for too long a time. They get oxidized to form peroxides, and these peroxides built as store the ethers for a long time. That's the reason why if you have a diethyl ether bottle sitting in your lab for too long a time, you better dispose it rather than use it, because it must have developed some peroxides, right? That's a disadvantage we have even with DHF. These days we put some stabilizers to stop this process, but nevertheless you have to be careful if a bottle of ether is too old to use. Okay, because they form explosive hydrogen peroxides. Otherwise ethers are pretty inert. If you don't expose to air and oxygen, to sunlight, you are So we talked about ethers as a protecting group, right? So whenever you talk them as protecting groups, you need to be able to deprotect it at the end of the day, right? For example, here the phenol has been protected as ethyl ether, so or ethanol is protected as a phenyl ether, so it can be regarded both ways. You can cleave them back to respective groups. This was the reverse way of making ether. Remember, if you have an alcohol and an alkyl halide, you can make ether using Williamson ether synthesis. Now we are trying to go reverse. How do we cleave the ethers? Is there some chemistry for ethers, right? That's something. So if you use strong acids like HBr and reflux them at high temperatures, the bromide would act as a nucleophile, and that would attack this alpha position of the ether, the less substituted position. Not this is sp2 carbon anyhow. If you have two sp3 carbons available, it would go to the less substituted carbon and attack this CH2, so that this bond breaks, and then that gets the proton and becomes alcohol, right? So you liberate your alkyl halide plus alcohol. That's called cleavage of ethers, right? Ethers are generally unreacting. However, if you use a strong acid, you can cleave them at elevated temperature using strong acids such as hydroiodic acid or hydrobromic acid, and you can generate alkyl halides through the SN2 reaction. Okay. If you have tertiary ethers, you would undergo SN1 reaction, right? So here is an ether where you have a primary alkyl group on one side and a secondary alkyl group on the other side. So you are using HBr. So HBr would attack on this methyl group and it would cleave this ether bond. It would become an alcohol on this side, but that you have excess of HBr, so that alcohol in turn becomes a bromide, so you get two bromides. Okay. You cannot get alcohol here, but in the previous slide we got alcohol because this is sp2 carbon. You cannot substitute this alcohol with another bromide, but if this were to be sp3 hybridized hydroxy group, you can substitute that with a bromide HBr. Okay, so that's what we talked about in alcohols. Alcohols can be converted to alkyl halides using acids, especially hydrobromic acid or hydroiodic acid. So the same reaction is in play here, just that you don't have alcohol as a starting material, you have an ether. Ethers are cleaved to alcohols and alkyl halides, and whatever the alcohol that is formed, that itself undergoes another substitution reaction, giving another bromide, so you get two bromides. What's the mechanism? The mechanism is shown here. The first step is the protonation of oxygen using that's why we need a strong acid. Once this ether oxygen is protonated, that becomes a good leaving group, and as a result the bromide comes around now and attacks at the less hindered alkyl group. It could have chosen to attack here and broke this bond from here, but however this is less hindered, so the bromide is attacking here. These electrons are pushed to the oxygen, so we got alcohol back plus bromide, but this alcohol is in presence of HBr, so this HBr doesn't just leave it alone, right? Again this protonates this hydroxy group, and that becomes a leaving group, and the bromide comes and attacks this carbon, and this water molecule takes off. As a result, you have another bromide molecule forming. So in short, you can cleave the ethers into respective bromides using strong acids. What if I have a cyclic ether of this kind? It would become dihalide, because one side it opens up, on the other side you have an alcohol, which in turn gets substituted, so you get diiodide here. Remember that these are very unreactive. You need the higher temperatures and a strong acid. Again, the mechanism: first step is protonation of the electrons, using the electrons of the oxygen, and that becomes a leaving group. So it attacks, iodide attacks on one of the carbons because these two are symmetrical. So this ring opens up, you got an alcohol on one side, iodide on the other side, but this thing again undergoes substitution reaction with excess of iodide, and as a result you get at times this could be reversible if you are in a basic medium, but in the acid medium you have too much of acid, so you are only going in one direction. You get diiodide as a byproduct. Okay, sorry, as a product. This is diiodobutane. Right? So that's why when you use strong acids, you don't use ethers as solvents. And there is another reaction which is especially specific for aryl allyl, right? Allyl. This is allylic position, and this is allyl ether of the phenyl alcohol, phenol. So phenyl allyl ethers, upon heating, undergo rearrangement or reorganization of the electrons. That's why it's called rearrangements. So you push these electrons here, and this bond is broken to here, and this bond is coming back here. This is called a pericyclic reaction. We'll see, look into the mechanisms and other things when you get to the pericyclic reactions. That's chapter 30. For now, just remember that there is some chemistry to phenyl ethers of allylic alcohols, or allylic phenyl ethers undergo Claisen rearrangement upon heating to higher temperatures. This was invented by a scientist called Claisen. So these are called Claisen rearrangements. Okay, and normally this group transfers to the ortho position of the substitution. If you have this is the ipso carbon, you get substitution at the ortho position. If the ortho position is substituted already, it doesn't stop here. It further undergoes rearrangement to all the way to the para position. Okay. So that's called ortho-para Claisen rearrangement. Now here you have an ortho substitution free, so you get allyl group transfer from oxygen to carbon. That's a rearrangement, right? So how do we make allyl ethers? You take phenol, convert it into phenoxide, do a Williamson ether synthesis using allyl bromide, you get allyl phenyl ether. This is easy to form, carbon-oxygen bond. Now you transfer that into a carbon-carbon bond. That's the beauty of this rearrangement. You form an easy bond and you transfer into a difficult substitution, right? So this reaction has found wide applications in natural product synthesis. Whenever you want to substitute benzene ring in ortho position, you think of Claisen rearrangement. So now it brings us to the chemistry of epoxides. If you are familiar with all these concepts that we talked about, the chemistry of epoxides they can be very easy. Okay, otherwise please review the chemistry of ethers before we go into epoxides, because epoxides are also kind of ethers, just that they are in the cyclic structures, right? This is ethylene oxide. This is also called oxirane. You see, if you draw the electron map of it, you get to see that electron density is mostly centered on oxygen. These are the electropositive centers. So if you were to do some chemistry, if you have a nucleophile, you get nucleophilic opening of these rings, and these electrons are pushed onto the oxygen because oxygen is electronegative, and you can do substitution reactions and ring opening reactions on oxiranes. Okay, first of all, how do we make epoxides? Epoxides are made by oxidizing the alkenes, right? That's why these are called ethylene oxides. Ethylene is undergoing oxidation and then getting oxygen, so ethylene oxide. And why are these epoxides more reactive than ethers? We talked about ethers chemistry. Ethers are not as reactive, but epoxides have some reactivity inbuilt because of the ring strain. Because of the ring strain, they have inbuilt strain energy. They want to release that strain. They are unstable. When something that is unstable is more reactive. See, as such, it has 25 kilocalories of strain, ring strain built into the ring, because you're trying to form a ring between three atoms that has a lot of torsional ring strain, right? So when you have a nucleophile, strong nucleophile, this can attack on this carbon and this bond can break, and the activation energy that is required for the reaction is very low. If you want to do the same reaction in a diethyl ether or dialkyl ether, which is not a ring, so you have a higher activation energy to cross. The reason why ethers are not as reactive as cyclic ethers are. Okay, so that's the ring strain. The 25 kilocalories ring strain that is built into this ring is trying to relieve itself by undergoing this reaction. So you don't have much of activation barrier for that reaction. So epoxides are good synthetic intermediates than ethers. How do you make epoxides? Epoxides can be made by using this peracid. Peracid is donating one of the oxygens to alkene. In other words, alkene is a nucleophile that is attacking this electrophilic oxygen. This oxygen, this is electrophilic carbon, but this is oxygen is not electrophilic. So if you use just a carboxylic acid, this will not be done. You got to use this peracid. Peracid is source of oxygen here. So this pair is attacking this oxygen. As you can see here, this is alkene. It's called butterfly mechanism of epoxidation using peracid. It could be any peracid. It doesn't have to be benzene ring. It could be even peracetic acid. R group is just an alkyl group or an aromatic ring. What is more important is this peroxy group. This alkene is attacking this oxygen and this bond is broken, these electrons are pushed onto the oxygen, and that becomes a oxide, and that oxide abstracts as hydrogen. So there is another pair of electron on this oxygen, so that comes back and takes care of the positive ion here. So as a result, you have epoxide. If you have cis alkene, you get cis epoxide, right? If you have trans alkene, you get trans epoxide. What is the byproduct? The byproduct is acid. This is peracid and this is just acid. Okay, so the colors are kind of representative here. This oxygen, which is red in color, is becoming a hydroxy group. The black oxygen is now becoming carbonyl. So that's kind of tells you. If you were to label this with isotopic atoms, you would find out this is O18. If this were to be this were to be O18, and anyhow there is a resonance in this thing. We don't want to discuss too much about the mechanism here, but just to let you know that this undergoes through a Kriege butterfly mechanism. Kriege is the scientist who came up with this mechanism the first time. So if you want to convert an alkene into epoxide, you use peracid. You can even use hydrogen peroxide sometimes, but these are more convenient than hydrogen peroxide. These are much milder. They can be weighed on a balance and they can be used, so it's much more convenient than hydrogen peroxide. And the byproduct is carboxylic acid, so you can easily wash them off with bicarbonate, so you get epoxides more or less in pure form, and you can either purify if you want to, or you can proceed further. These are very reactive intermediates. So this is a cis alkene, so you get a cis epoxide here. This can also be regarded as epoxy heptane, epoxide. This is an epoxide or oxidane. So epoxides have some chemistry, especially they have ring opening reactions, because they want to open the ring and relieve the strain. There is a lot of strain in the ring. So when you use acids, there are two types of ring opening reactions. One that can be done in acid medium, one that can be done in basic medium. In acid medium, you are activating the epoxide for the nucleophilic attack. Your nucleophile is neutral, right? So you're using acid and this epoxide is getting protonated, so you're activating your electrophile. So there are two electrophilic sites when you have unsubstituted epoxide. This is methylene, this is methyl containing methylene. So this center is a tertiary center compared to this one, right? So when you have choice of opening from two sides in the acid medium, there is much of electron orbital overlap in this direction, so there is more positive charge on this, because that's where the positive charge would be stabilized than here. So this is more electrophilic, and as a result the nucleophilic attacks at this center and this opens up, so the hydroxy group becomes attached to this methylene, and as a result you get substituted compounds in this carbon. Okay, so if you were to write the other side product, if you were to attack here, you would get a different product. You would get a regioisomer of this. So you have to be careful. If you are doing an acidic medium, you get opening from a highly substituted epoxide terminus. If you are doing in a basic medium, you get to attack on this side. So depending upon what you want and what you have, you can choose your medium and your nucleophiles and your reactions. Okay, so the mechanism involves protonation of the oxygen. Thereby you are activating the electrophile. Your leaving group is activated as well, so your nucleophile is now attacking at the highly hindered carbon, which is a weak nucleophile. This is similar to opening the bromonium ion that you learned in alkene chapter. There you had bromination. The first step is bromonium ion. When you do the bromonium ion, if you are opening with another nucleophile, like say water, you would get Markovnikov product, right? So the same is true here. And what happens to the stereochemistry? The stereochemistry gets inverted because this is an SN2 reaction. Your methyl is now, the center is inverted because this is attacking from the other side of this phase. So this hydroxy group and the incoming nucleophile are on two different sides, and the chiral center also gets inverted. If you were to label this as R or S, you would see that this center has been inverted. So how about if you do the ring opening reaction in a basic medium? In a basic medium, there is no protonation of this oxygen, so you are not activating your leaving group, you are activating your nucleophile. In the previous slide we had a neutral nucleophile. Here we have a very strong nucleophile because the base is abstracting the proton from this methanol and methoxide is formed, so the nucleophile is getting stronger. Now it's undergoing a substitution reaction, and this substitution reaction favors a less hindered site because this, now the charge on these two carbons is same as one another, so this is not preferred. This highly substituted is not preferred over less substituted. This doesn't wait for it to build the charge here, it rather attacks on this side, as a simple SN2 reaction would do, and as a result you would get ring opening from a less hindered site. This is simple SN2 reaction, just remember that. Okay. So no protonation to produce a good leaving group, no resonance. As a result, ring can open because of the strain only, and the nucleophile is stronger, and that would attack on the less sterically hindered carbon. That's all happening in a basic medium. So again, the stereochemistry wise, the hydroxide gets attached to this carbon, the ring, this is oxygen that gets attached to this highly hindered carbon, and the incoming group is attached to that carbon. Both are going in opposite direction. The chiral center, whatever you have here, would be inverted. The chiral center, whatever you have here, would be retained. So if you were to assign R and S nomenclature here, you would see, what if you had a S here, you would still have an S here. If you had an R here, it would have an S here. Okay, so you have to not only look at the terminus of opening, is it less hindered one or highly hindered one, and you also have to pay attention to the stereochemistry. Okay, so there are two things to remember. In acidic medium, you get the ring opening from a highly substituted epoxide terminus. In a basic medium, you get the ring opening from a less hindered carbon. See, these are the two carbons of the epoxide. This is highly hindered carbon or highly substituted carbon or less substituted carbon, and depending upon the medium you can choose to go with the less hindered site or highly hindered site. In the acid medium, you open from a highly hindered site, attack on the highly hindered carbon, and ring opens on the other way around, and same is true here, just that it attacks at the less substituted carbon. So you can change the nucleophile and you can make a lot of ring opened compounds like this. Okay, so you can see some of the things that are done here. This is an epoxide which has a highly substituted carbon on this carbon and less hindered carbon here. So if it is a basic medium, your nucleophile is stronger, so it's attacking at the less hindered substituent site. You get alcohol as shown here. It doesn't matter when it's hydroxide because both the groups are hydroxides, but if it is alkoxide, you got to be careful in writing your product because alkoxide get attached to the less hindered carbon. Okay, for example, in this case you have methoxide, and whatever is happening here is happening on the less hindered carbon, and the hydroxy group attaches to the highly hindered carbon. Your incoming nucleophile is attacking to this carbon, so that's attached here, so you have to be careful. And initially these electrons are pushed here and alkoxide forms, but you have methanol as a medium, so the methanol or water, when you add water, gets protonated. That's called workup. You get ring opened products. Okay, in basic medium there is no protonation. When you write the mechanism, you have to make sure that you only have anions, you don't have protons, so you don't get protonation. In acidic medium you have protonation and you have neutral nucleophile, similar to bromonium ion, right, that we already talked about in alkene chemistry. So if you know whatever the bromine chemistry that you did, you would be able to write these reactions as well. When you have symmetrical epoxide, normally you can get away without knowing the regioselectivity, but when you have substituted epoxides, you need to know your regioselectivity, right? So that's something you have to see. Let's go back to this one. See, we missed some things here. Reaction ring opening of epoxide is similar to ring opening of bromides, right? And as a result, you can make alcohols. Here, if you use water as a nucleophile, you can make diols, but notice that the stereochemistry of the diols is trans to one another, so you can make trans diols. If you were to make cis diols, you would just take an alkene and do dihydroxylation, you would get cis diols. If you were to make trans diols, you would take alkene, go to epoxide, and then ring open it so that you can make trans diols. Okay, so depending upon the structure of the diol you need to make, the alkenes can be used accordingly. And this ring opening chemistry is similar to that of bromonium ion chemistry that we learned. And Epoxides can be opened into halohydrins as well. If you use a halide as a nucleophile and it attacks on one side, and you make halohydrins on the other side. I can go from halohydrin to epoxide. Here I need to just use these electrons and then attack this carbon, and this would be a leaving group. That's called intramolecular SN2 displacement. So the halohydrins can be produced from epoxides. Epoxides can be produced from halohydrins. That's what I was trying to say. See, you have an alkene. When you remove the chlorination in water, you get halohydrins, right? That's making a chloronium ion. Water is acting as a nucleophile and it's opening. So as a result, you make halohydrins that you already learned in Chem 251. So if you were to make epoxide, let's say if you were to treat this with sodium hydroxide, this would pick the proton, and this is a good leaving group, so that would attack internally, and this would leave. You can make epoxide out of it. So I can go either ways. I can go from epoxide to halohydrins, or from halohydrins to epoxide, depending upon the need of the synthesis. And this is called intramolecular Williamson ether synthesis, because everything is happening within one molecule. Alkoxide, alkyl halide, substitution, everything is happening within the molecule, so it's intramolecular. If we have a if you have an alcohol and bromine, if you have an alcohol and an alkene in the same molecule, and if you use bromine, you can make cyclic ether, but that is through the bromonium ion, right? So that's kind of halohydrin reaction. Anyhow, we are talking about epoxides. Let's get back to the epoxides. So epoxides can act as electrophiles depending upon the substitution pattern. They can either be opened at a highly substituted carbon or a less substituted carbon. In this case, it's both are same, so it doesn't matter. We already saw that they can be opened with the nucleophiles. In basic medium, nucleophiles are stronger, so they open at a less hindered site. In acidic medium, nucleophiles are weaker, so they open at a highly hindered site. What about Grignard reagents? We saw briefly about the Grignard reagents in the alkyl halides. So the Grignard reagent can be generated using the alkyl halide. This is R minus, and this is a nucleophile, and this is an electrophile. So if you add this nucleophile to the electrophile, this is doing a substitution reaction. It's adding here, and this is opening, and as a result you get ring opened alcohol. And notice that the two carbons are black in here are coming from epoxide, so you can make extended alcohols from Grignard reagent. If you were to use a formaldehyde, you would only have one carbon. If, say for example, you want to extend your Grignard reagent by 2 carbons and you want to make alcohol, then you can use only epoxide. You cannot use any carbonyl compounds, because the carbonyl compounds would give the alkyl groups attached to the same carbon as that of hydroxy group. Here the hydroxy group is attached to one farther away carbon, two carbons farther away from the original alkylating reagent, right? Or Grignard reagent for that matter. So you can make bis-homologated alcohols, so to speak, in the side chain. How about cyclic epoxides? Let's say you had cyclopentene, you epoxidized it using metachloroperbenzoic acid, MCPBA. You made this cis epoxide. Now you are adding methyl magnesium bromide to it. Both sides are equal, one and the same, so it doesn't matter whether you attack from here or from here, but you have to be careful when it is substituted. So anyhow, let's attack it here, and then the electrons are moved into oxygen. That forms the magnesium oxide, and the methyl group is coming from the opposite face to this epoxide. So that's what you need to remember. The leaving group and the incoming group are on different planes, so you get trans alcohol. Okay, so and here is the case more complicated. You have substituted epoxide. One side it's highly substituted, the other side it's not substituted. You have two ways to open it. You can open it in an acidic medium using a neutral nucleophile, or you can use it in a strong basic medium where you have an activated nucleophile. In this case, this would attack from lower substituted carbon end, so you get highly substituted alcohol group, and both are going in opposite directions. In this case, this would attack, this methanol would attack from the highly hindered carbon, so your hydroxy group get attached to the lower substituted carbon. Okay, so you can make regioisomers of the compounds. Here I have a terminal ether, here I have an internal ether or substituted ether, right? So yeah, I have an internal alcohol or a tertiary alcohol, Here I have a primary alcohol starting from the same epoxide, almost using similar type of nucleophiles. Constitutionally they are same. Sorry, molecular formula wise they are same, but constitutionally they are different. You are making epoxides, right, opening both in two ways, so you make two different products. So you got to be careful. They're giving isomeric products, right? So what is the synthetic use of epoxides? So you can use various types of nucleophiles. You can use hydroxide as a nucleophile, you can use acetylide as a nucleophile, amines as nucleophiles, you can use hydride as a nucleophile, you can use nitrile as a nucleophile, thiol as a nucleophile. As a result, you can make various synthetic compounds. So epoxides are considered to be very synthetically useful intermediates. Unlike ethers, simple ethers, acyclic ethers are not as useful as cyclic ethers. Especially epoxides are more useful than any other cyclic ether. If I use water as a nucleophile, I make diol. If I use acetylide, I can make a carbon-carbon bonding. This is a strong nucleophile, so it's attacking from a less hindered site, so you get this kind of an alcohol. Amines are basic, so you are opening from a less hindered site. Again, this hydride is a strong nucleophile, again you are opening from this site. Nitrile is also a strong nucleophile, so you are opening on this site. Thiol is a strong nucleophile, again you are opening on that site. Okay, so you can make thiols, nitriles, amines, all kinds, alcohols, and so on and so forth. You can use this as for carbon-carbon bond forming. You don't have to remember this, but you have to understand that you can use these epoxides in your synthetic schemes to make something that you want. So this in turn connects to alkenes, so alkenes can be used in many various ways through epoxides. So there is more chemistry to alkenes just because of epoxides. That's something you need to remember. So let's summarize this. Whenever you want to plan a synthesis using epoxide, you have to make sure that epoxide opens in opposite phase from two different phases. The alcohol that is producing goes in one phase, the nucleophile comes from the bottom phase, you get trans compound, and also there are two carbons between the nucleophile and the hydroxy. Right? The hydroxy is not attached to the same carbon that nucleophile gets attached to, because the bond breaks, and then as a result this gets attached to the other one. Okay, so you got to recognize that pattern, that two carbons, one carbon is attached to hydroxy, the other carbon is nucleophile. Normally this is always hydroxy because you are opening epoxide. Then you can later on convert this hydroxy group into something else that you want. So it's very synthetically intermediate. So if you have something like that, you can think of the epoxide. Electrosynthetically you can think of an epoxide. Whenever you have this kind of connection that you want to make, a nucleophile and a hydroxy group or two carbons away from one another, you can think of an epoxide in your synthetic schemes. Okay, so for example I have this epoxide, I'm opening this with a nitrile, so I can make nitrile and an alcohol containing ethane. Ethylene is the bridge. Okay, that's something you have to remember. Methylamine is opening this epoxide, this is symmetrical epoxide, doesn't matter, so I'm getting ethylene bridged 3 carbon compound, 2 carbon compound, right? So alkane is opening, again I'm getting homo-proporgyl alcohol. If I have an alcohol group here, that's called proporgyl alcohol, so I'm getting homo, it means one more carbon than I would have got from formaldehyde or whatever the electrophiles that we used in Grignard reactions, right, in other day. So that's something you have to remember. When you use epoxide, you get 2 carbon extension, and you can use various types of nucleophiles. You can use carbon nucleophiles, you can use amine nucleophiles, you can use oxygen nucleophiles. You can go on to make more synthetically useful compounds. For example, this amine can be further used as a nucleophile, one more equivalent of epoxide, you get a diol. This diol can be dehydrated to an ether that we talked about in using a strong acid, or you can convert this diol into dihalide and then again use another nucleophile. So this can be an electrophilic carbon now, this is another electrophilic carbon, so cyclic amines can be made. So there is no end for the creativity here. You can keep on using these intermediates as much as you want, as long as your creativity allows, as long as you can plan an epoxide in your synthetic scheme. Okay, so That's that. And there is another, there is commercially available epoxy which is called epichlorohydrin. Not only you have two centers now to functionalize, you can get one more center from commercially available starting material. So now we have three carbons to functionalize. So this compound is very well used in organic synthesis. If you have nucleophiles, you can selectively substitute this chloride because that's more reactive than epoxide. And if you heat it in presence of nucleophile, or if you force it, you can open this nucleophile again. Depending upon the basic medium or in acidic medium, you can open either from the less hindered site here or highly hindered site. As a result, you can make lot of derivatives out of this commercially available compound. Okay, so you can get two nucleophiles attached to two different carbons, which are three carbons away from one another. That's another thing that you can cache upon the epoxide that is already containing another nucleophilic center, electrophilic center. Okay, so I'm going to skip some of the slides just to give you an example where the stereochemistry is involved. This is a highly substituted carbon, this is a less substituted carbon, and this is a basic medium, and this is a nucleophile. So the actual nucleophile is a hydroxide. Hydroxides in the strong basic medium attack from a less hindered site. So this is the site they are attacking with. So this center doesn't get changed. That center remains as is. What's happening to this center? This is not chiral center, so there's no chirality, so that just gives a primary alcohol. When I have an acidic medium, when I have a neutral nucleophile, water is acting as a nucleophile, the hydrogen is protonating the oxygen, and the water is attacking from a highly hindered site. As a result, I make a tertiary alcohol, but notice that the stereochemistry is inverted because this is attacking from a bottom phase then to the leaving group 180 degrees away from the leaving group, SN2 substitution. As a result, I get this kind of an alcohol which is inverted, right? What about if I have a nucleophile within the molecule? Would it do anything? So that's something I need to think of, right? So first step, I would substitute this bromide with methoxide here. That methoxide can act as a nucleophile intramolecularly, so that would attack on this side. So depending upon its neutral or substituted neutral or basic medium, I can open the ring from that side, or I can open the ring from this side. And here the methoxide is opening, the epoxide is opening from less hindered site. So the intramolecular methoxide is going from here to that. Okay, let me correct myself here. So the methoxide is acting as a nucleophile, and it's in a basic medium, so it's attacking on a less hindered site, and whatever the O minus that is produced here, that is attacking this bromide, and then that's leaving. So I'm getting this kind of a compound. So the first step is not on the bromide, it's on this one, this epoxide. Okay, so that's the mechanism. You can draw them out. I'm not drawing because I don't have stylus today. So this is the mechanism probably that we talked about in the previous slide, that's attacking there, and this epoxide is opening, and that hydroxide is attacking the internal electrophilic site, and this is the leaving group, and as a result this is intramolecular substitution. The first step is intermolecular substitution, and you get cyclic ethers. Can you write a mechanism for this? You have water and you have acidic medium, so the ring opening is from the less from highly hindered site, and the first step is where you're producing an alcohol because you have an alkene, right? This alkene can undergo hydration in presence of this water, and not only that, this also can undergo ring opening. So you have to think of as to which one is happening first. So to me it seems that there's something that's attacking from here to here. How did I make carbon ion here? So the first step is, let's say, hydration of this molecule. You get Marconic of alcohol, and that carbon somehow is attacking this carbon, and that's leaving. I just don't have any clue on that. Anyhow, ask me about this in the next class as to how on earth are we forming the carbon-carbon bond. I would imagine that there is an oxygen here and there is a methyl group here. There seems to be some typo here. So this is dimethyl and this is an oxygen. Then I can write a mechanism for that. So about thiols, we talked about sulfides, ethers, epoxides. We skipped a little bit of thiols. There are a couple of concepts that we need to talk about. Though they are structurally similar to alcohols, they have distinct properties, especially the physical properties. They are very smelly compounds. Sulfur has expandable oxidation, so you can make sulfur oxides out of it. And they are part of peptides because of the amino acid that is called cysteine and methionine. Okay, so you would see very biological significance for thiols. Thiols and sulfides are more volatile because of the less hydrogen bonding. Though sulfur is on the same group as oxygen, it's not more electronegative than oxygen. The electronegativity is more or less same as oxygen, and they are more polarizable. They are good nucleophiles, but they are not strong hydrogen bonding donors or acceptors. As a result, you don't see that much of hydrogen bonding. That's one of the reasons why hydrogen sulfide is a gas, whereas hydrogen oxide, that is water, is a liquid, right? So they are more volatile, they are very smelly, skunky. Hydrogen bonding is less important for thiols compared to alcohols. Dipoles are less pronounced. Thiols are more acidic than alcohols. Because of the polarizability. Size mismatch between the small and hard proton and large polarizable sulfur atom favors the formation of thiolate anion. That's what is responsible for the increased acidity of thiols compared to alcohols. Thiols are also good nucleophiles, as I said. Thiolate is used as a nucleophile here. So that's attacking this carbon and this bromide is leaving. As a result, you can make thiols. So that's one of the ways you can make thiols. If you already had an R group here, you would make thioether, that is disulfide, right? That would be like Williamson ether synthesis. Another way of making thiols is to use thiourea as a sulfur source. The advantage of this is that thiourea is not as smelly as simple thiol is, and this can act as a nucleophile, and the sulfur as a nucleophile that's attacking this methylene carbon, and then that bromide is leaving. There's a substitution reaction, but still this whole thing is attached to sulfur. Sulfur is donating its electrons, so that becomes sulfonium ion, and this sulfonium species is now hydrolyzed using sodium hydroxide. Hydroxide ion attacks this carbon and this leaves. As a result, you get thiol. Okay, and the urea is regenerated. You started with thiourea, you get urea. That means sulfur is lost. Sulfur is acting as a nucleophile. The bromide is substituted, so you get thiol. So you can use thiols, sulfides. For example, hydrogen sulfide can be used as a nucleophile. You get thiols, or you can use urea as a nucleophile, or you can use potassium thioacetate. This is potassium thioacetate, that is also sulfur source. So what is important? You should have a good leaving group like bromide. Here chloride, the chloride is generated using auxiliary chloride. That's one of the alcohol reactions. You can also use sulfonyl chloride, thionyl chloride to convert alcohols into chlorides. And now this sulfur is acting as a nucleophile because S minus K plus, right? This acetate is just a protecting group on it, so later on you can remove that using base. Okay, that's hydrolyzed to get the thiol. So potassium thioacetate is used as sulfur source. This is again similar chemistry here, just that the nitrogen is activated into a good leaving group by this diazotization that you learned in aromatic chemistry. Aniline is not this amine is not a good leaving group, but when you convert this into a diazo group, you can do substitution on this carbon, that's sp2 substitution, and as a result you can make thiols. Okay, and If you have thiols, you can make disulfide bonds using iodine. That's chemistry that is normally goes on in the hair. Your hair gets interlocked because of the sulfide bond formation. Thiols are normal. Most of the proteins, a lot of proteins exist in this disulfidic form bonding formation. They have sulfide linkers, and the enzymes normally cleave this bond. So that's what you learn in biochemistry. Anyhow, thiols can be converted into disulfides. Why do I call disulfide? Because there are two sulfurs. If there's only one sulfur, you call them as sulfides, right? So the other reaction of thiols is that they can act as nucleophiles, so you can make sulfides as shown here. This is the thiophenol. This is attacking this is electrophilic carbon, and this is leaving, so you can make methylphenyl sulfide. This is the same as like ethers that we made, right? Williamson ether synthesis. And ethers, we didn't see this kind of chemistry there, but here sulfides act as nucleophile, and they can alkylate themselves by substitution reactions, and as a result you make sulfonium ions, sulfonium salts. Whereas in ether case, these salts are not very stable, so you don't see alkylation of diethyl ether, but you see alkylation of sulfur giving stable sulfonium salts. So that gives some chemistry to the sulfur than compared to the ethers. Okay, we have sulfonium alloys, but we don't have you don't see this very reactive. Okay, so anyhow, this you will learn the use of these salts in advanced classes. At your level, it's enough to know that sulfides have some chemistry that ethers do not have. Okay, and they can be oxidized further. As I said, ethers cannot be oxidized further because oxygen does not have empty orbitals, but sulfur has. So as a result, sulfurs can be further oxidized. You can expand the oxidation states. This is sulfur plus 2, this is sulfur plus 4 oxidation state, and some of these reagents are used as solvents. This is called polar aprotic solvent, dimethyl sulfoxide. Polar aprotic. Why is it polar? Because you have a dipole. So unlike ethers, sulfides can be oxidized. Sulfides can be alkylated. That's something you have to remember. In ethers case, we don't have that kind of stable species, right? In sulfides case, we do have stable sulfoxides. This is what we saw in the previous slide, right? So anyhow, they are good nucleophiles. They can be alkylated, they can be oxidized, and that's it. How about the spectroscopy? Now that we learned the NMR, we need to look at the NMR of ethers as well as sulfides. Oxygen is electronegative, so the hydrogens that are attached to the carbon that is next to ether, oxygen, is kind of downfielded a little bit. Let's say if you have methane, you get around 1, methane is 0 to 1, right? So TMS is at 0. But if that methane is dimethyl ether, you would see a downfield shift of that protons on the carbon. They go up to 3.4 to 4.5. And in the epoxide case, the hydrogens that are attached to carbons are absorbed anywhere between 2.5 to 3.5. Again, this is because of the electronegativity of the oxygen. So there is de-shielding effect because of the oxygen, and you see the peaks for ethers around 3.5. How about in carbon NMR? Carbon NMR, they go up to 50 to 80 depending upon the structure of ether. Okay, again the de-shielding effect of oxygen can be seen. In the IR spectrum, you see a peak for C1, the single bond was stretching between 1050 to 1150 centimeter inverse. Okay, with that I'll stop here, and that's about ethers and epoxides, thiols and sulfides. You have to practice some problems, and if you have any questions, please get back to me on that. Thank you.